This is part 4 of the calculus section of our aeronautical engineering course. We can use calculus to determine the strength of a beam with a rectangular cross-section. See, like this one, if we were to cut this 2x4 board here down the middle, we would say our cross-section is 2 inches by 4 inches. Now the cross-section of this pen, if I were to cut it in half, it would have a round cross-section. But a 2x4 board has a rectangular cross-section. Okay, let's look at a 2x4 wooden board that's standing on edge. See, this is on edge. If it were lying like this, like a scaffold board, that wouldn't be standing on edge. And obviously a 2x4 is stronger this way than it is turned over as a scaffold board. So we're going to look at this one, which is standing on edge. Okay, like a floor joist would, or a rafter, or a ceiling joist in a house, or a wing spar. Okay, first let's figure this board's strength by using the non-calculus method. Let's calculate the contribution of each 1/8 inch sliver. The top half of the board has 16 slivers. I drew a dotted line at the center of the board, and there are 16 lines there, with the top line being the 16th line. I've divided this top 2 inches into 16 little 1/8 inch high slivers. They're 2 inches across by 1/8 inch high. Okay, so the area of each sliver is 2 times 1/8, which is 2/8, which is 1/4 of a square inch. The stress of the wood at the top and bottom of the board, okay, the stress up here and the stress down there, is more than the stress in the middle. Actually, there's no stress in the middle. Well, there's shear stress in the middle. That's the topic of another lesson. But as far as the bending stress, there is none here in the middle. The top, like if you had this board, let's see, okay, and we're sitting on a fulcrum, and here's somebody teeter-tottering on this side, and here's somebody else teeter-tottering on this side. Well, the top of this board would be in tension. The bottom of this board would be in compression. Okay, the wood at the middle of the board, in the center of this board, see, there's the top, that's in tension. There's the bottom, it's in compression. This wood in the center, it wouldn't be in tension or compression. Okay, let's look at the force that the top sliver withstands and multiply this force times its distance to the centroid line. So we're going to calculate the force of this top 1/8 inch sliver. We're going to multiply it times its distance to the center so we can figure out its bending moment contribution, how much it contributes to the strength of this board. See, this top sliver being the top 1/8 of an inch of our board right there. Okay, let's say this is a sugar pine board and is stressed to its ultimate limit of 4,460 pounds per square inch. Okay, sugar pine. Okay, ultimate means that's what it breaks at. A good engineer would never allow a load that would come near breaking it, but that's what we're looking at, what it takes to break it. Okay, the stress in the top of the top sliver is 4,460 pounds per square inch. Okay, here's our top sliver. I'll go ahead and darken it in. Let me go ahead and draw it here. A lot bigger. Okay, that looked like this here. This is 2 inches. This is 1/8 of an inch. Okay. Okay, the stress in the top of the top sliver is 4,460 pounds per square inch. So right at this point, there at the top of the sliver is 4,460 psi, or pounds per square inch, whatever you want to call it. Okay, but the stress at the bottom of the sliver down here isn't, which is right there. Okay, this is a drawing of this top sliver. The stress here isn't quite as much as the stress up here at the very top. The stress here isn't quite as much as that. So, okay, so how much do you figure it is? It's closer to the center of the board. That's why it's not stressed as much. The further the wood gets from the center, the more it's stressed. Okay, the stress at the bottom of this top sliver, which is 1 7/8 inches above the centroid line. See, let's say this is our centroid line. This is 1 7/8 inches from the bottom of our top sliver. 1 7/8 inches from there to there. Okay. So the stress at the bottom here is going to be the stress at the top times that distance over that distance, which is 2 inches from the top of the top sliver to the center. So 4,460 pounds per square inch times 1 7/8 over 2. That's the stress right here at the bottom of our top sliver. And upon multiplying that out, we'll get 4,181 pounds per square inch. Okay, so that's the stress right there at the bottom of our top sliver. Stress at the top is 4,460. Stress at the bottom is 4,181. Okay, but what we want to know in order to calculate this top sliver's contribution to the strength of this board is what is the stress in the middle of the sliver. Well, let's just take the difference. Let's just average them, 4,460 and 4,181. Or we could just say use this distance, which is halfway between 1 7/8 and 2 inches. It would be 1 7.5/8, which is 1 15/16. 1 15/16 from the middle of this top sliver to the center of the board. And we can say the stress is 4,460 psi times this distance, 1 15/16 inches, equals 4,321 pounds per square inch, because well, actually this is 4,460 times 1 15/16 over 2 inches. So 1 15/16 over 2 is almost 1. So this is almost 4,460. We have pounds per square inch times inches over inches, which leaves us with pounds per square inch. So there's our stress, 43.21 pounds per square inch at the center of our top sliver. So the force that is withstood by the top sliver is equal to the stress in the top sliver times the area of the top sliver. So looks like we're going to need more room. Hold her just a second. Okay, the force that is withstood by this top sliver is equal to the stress in the top sliver, which we figured out just a second ago, 43.21 pounds per square inch, times the area of the top sliver. Well, the top sliver is 2 inches across, 2 inches from there to there. It's 1/8 inch up from there to there. So that's area equals 2 times 1/8, which equals 2/8, which equals 1/4 of a square inch. Okay, so the force in this wood that is in tension or compression, depending on whether it's being used as a teeter-totter or a table, this force is equal to its stress times its area, which is 43.21 pounds per square inch times 1/4 of a square inch, which equals 1,080 pounds. Okay, the distance between the middle of the top sliver and the centroid of the 2x4, okay, this distance from the middle of the top sliver right there, from there to there, that was 1 15/16. So the bending moment contribution of the top sliver is its force times that distance, which would be 1,080 pounds times 1 15/16 inches. Which gives us 2,093 inch-pounds of bending moment contribution. The numbers change a little for calculating the contribution of our next highest sliver. Okay, we just calculated this top sliver. What about this sliver between there and there? Okay, it has the same area, 2 inches by 1/8 of an inch. The stress in this top sliver is going to be the stress at the very top times our conversion factor, which is that distance from the middle of the next highest sliver to the center divided by the distance from the top to the center. So it'll be somewhat less than 1. It'll be smaller than it was on the top sliver. So it is 2 inches times 1/8 of an inch, that's our area, times our maximum stress, 4460 pounds per square inch, times our factor, that distance, over 2, which is 1 13/16 over 2. Okay, that gives us our force. Now we have to multiply that times the distance of this force from the center, which is also 1 13/16. It wouldn't be over 2 though, just be 1 13/16. Okay, and that gives us 1,831 inch-pounds.